this presentation. So our project is called First Step Coral, and I'm one of the team members from MIT. In addition, Idak Diaz, Martin Lorella, and Enzo de los Santos. So they're also either current college students there or former students. And then I'd like to acknowledge Dr. Tom Perot. He's our chief scientist. And Roderick Samonte, which I think you guys know also. He's a teacher here. He was a teacher here in Salle. He also is a part of our team. And our partners, the Sagay Marine Reserve and the Children's Museum in Sagay. So why are we doing this project? Well, it's because coral reefs are important and the marine ecosystems is very important for life here in the Philippines. Half of the 75% of all corals known to science are actually found within this triangle here on the board. It's called the coral triangle. And it's about half the size of the US in terms of total area. But in the Philippines, 60% of actually food protein is sourced from the reefs. So it's a very, very rich source of food for people, all over the country. However, 80% of the corals in this area are actually threatened by human activities, development, pollution, waste issues, and all sorts of different uses. And in fact, the key, or the biggest issue is in fact the Philippines is the #1 rank in terms of coral hotspots, which means that they have the highest marine biodiversity, as well as the highest marine threat due to human activity. A small pie chart that shows how much, or what's the status of coral reefs in the Philippines. We only have 4% of corals, basically excellent corals left. And typically that's found in Tubataha, the marine reserve there, or in other parts of the country. And the rest are basically under attack every day by overfishing, pollution, and different activities that I'll highlight later on. And so there's really a drastic need to save this resource because there's so little left, given that also the Philippines is the most marine biodiverse, so the richest in terms of fish density and coral species density. And so our project is currently located in the Sagay Marine Reserve. I'm sure lahat na po sa Sagay. And so our two locations of our project is currently one in the Carbon Reef, right in the center of the Marine Reserve, and the other one is in the Molocapo Reef, or Molocapo Islands. And the Carbon Reef is, the Marine Reserve is approximately 32,000 hectares of protected seascape. That means there's no large-scale fishing activities, so that can allow us to put in a project that would help the marine ecosystem. In addition, in Carbon in Molocapo, in fact, there's no fishing and no take zones in both places, so really our project can thrive further. So, some of the causes of reef destruction, overpopulation here in the Philippines. There's lots and lots and lots of people that want to utilize the reef resources. In addition, to go to the beach and have a great time there. Industrialization, there's lots of activities, to put up beach resorts, hotels, ports, and other things that cause the coral reefs in the area to get dredged over. Waste disposal, I think you guys are well aware of these issues. Cyanide fishing, dynamic fishing, I think two of the more popular or more, common reef destruction methods that we know of. Siltation is one big issue. So siltation happens when we cut off the forest up to the mountains, and the soil is trapped by basically the trees in the forest are now released when there's rain and causes the rivers to turn into basically brown mud flows, and then dumps it into the sea area, and essentially turns the entire mouth of the river area where the river is drained into like a brown area of water, basically sludge and water mixed in the sea area, and that traps essentially causes sunlight to not penetrate down into the reef area and causes the reefs to die because essentially corals need sunlight to actually survive via photosynthesis. So Molocapo, the site of our project, is one of the sites of our project. We did essentially initial surveying of the reef area. So we did a reef survey going around the place to the ideal site where we can put our first step coral, modules. And then Roderick Samonte and Dr. Bro pictured up here where they were actually the first ones in July to go around the area to look for the ideal site location. And then we chose the tower in Molocapo. If we go there, we'll find the reef station. That's actually manned 24 hours a day by something like that guard, so that nobody does dynamite fishing in the area. And So we decided to put our bio-rock structures. I'll show you more about these later, how we restore the reefs much faster and much better. And we put that right next to the World Hall Tower where it's guard. And then we had meetings with the Barangay Chairman and the folks over in the community, because without their help, even if our project's actually very good, we cannot move it forward because it's been stolen, or we have issues with breakage or people throwing dynamite again in the area, which will not help the marine resource or the conservation of it. And so then we did some construction activities to build our bio-rock modules. In addition, we partner with the Museo sa Bata sa Negros sa Sagay, and I encourage you all, and this is why you bring your class to Sagay and visit this museum. It's very nice. There's various, exhibits on corals, different marine ecosystems and mangroves, the deep sea, to the shallow waters, and various different, biology type activities that you can take a look at. And I think second year, most of all, or third year, I think biology and subjects of science. So why are coral reefs important? Well, they support, number one, marine life. They support human life as well. They're a place for nurturing, baby fish, and so it's a hatchery. It's a place where there's lots of, small fishes that hide there and feed there until they grow up and then they migrate to the deep sea. So it's a really rich storehouse of food and protein. It protects the coastal areas because when waves crash into the beach, typically what it does is it takes sand and brings it back down into the sea. However, when there's a coral reef right in front of the beach, it actually slows the wave down and prevents the erosion of the soil or the beach area. Of course, it provides us with food. However, again, the reefs are dying all over the world. And so that's really a big problem. And the statistics show that 65% of reefs worldwide are dying. As I've shown you in the Philippines, it's 95% now is dying. So it's even more critical here in the Philippines, given that there's really, really rich marine resources, at the same time, really, really high threat for it. So it's a confluence, the meeting point of two, unfortunate activities. One is very high threat, and the other one is very, very high marine resources. The importance of protection is really, really high. Any questions so far? You guys can ask me any questions or any time during the presentation. So I'll keep on going. So why are reefs dying? As I mentioned earlier, there's dynamite fishing, different activities like that. There's also the cause of higher water temperatures due to global warming. Are you all familiar about global warming? You know what so you know about that, okay. So global warming increases the water temperatures, which then actually causes the corals to bleach. Corals do not like temperatures above 30 degrees centigrade. So during the really hot summer months that sustain, the entire reef area water system essentially increases in temperature. And above this 30 degrees threshold, you actually have corals start to die out. And it causes the entire coral reef area to bleach or turn white. Because the coral polyps that live inside it that give the whole reef color actually start to die off. And then what you have left is essentially the calcium skeleton. And again, all the other issues like sewage, waste, dredging, dynamite fishing, so lots of reasons why reefs are dying. And so you can consider now Boracay, which is a really prime example for development gone uncontrolled, because there was really no control for the development when the tourists started coming. So initially it was a pristine forest, pristine coral reef area, a really pristine marine and land ecosystem. However, when the tourist industry arrived and people started building homes, cutting the trees down and really developing the place, they really did not, control for growth. The growth was rampant and fast, and there was not any management in the growth. And so there was a lot of, sewage basically going down into the reef area, which caused, high algae blooms, which then covered the entire coral reefs with algae, which basically suffocated the corals and killed them all. And so, that's one of the, lessons we'd like to, portray to you. We need to, of course, develop as a country, but as well as, develop in a managed and a controlled manner, such that we don't disrupt the environment too much. This is what happens when the coral reefs are covered now with algae. So the reef system is covered with algae, the entire surface is covered with algae. You don't see any, nice fishes swimming there anymore. It's just basically a matte green area, and all the reefs or the corals are actually underneath this green mat are basically dying or dead because they've been suffocated, they can't see the sun, and they can't feed off the nutrients in the water. So the algae comes in various different types and colors. Essentially what you see here again is, a symptom of that. Corals being covered by large amounts of algae, killing them, slowly. And so there you go, another vision or a picture of what you can see in an area where there's lots of sewage in the water that causes like high protein count, which then increases the algae growth and covers the entire system with basically blankets of algae. So bleaching is another, issue that I mentioned earlier due to global warming temperatures. And so that's essentially, a global problem. It's something that we can't stop. Not even the Philippines, by cutting off all greenhouse gases, will be able to stop global warming because China, India, the US is pumping out more carbon than we are doing. And in fact, what we'd like to show with our project is that with the First Step Coral Project, we can maybe improve the survivability of corals by applying the BioRock process that I'll show you much more later. And so here, what a coral would look like when it's bleached. It's completely white. There's no more life on it. It's just a skeleton. And so no more fish will feed around it because there's no more, small snails and shrimp that can actually live on the ecosystem. Disease or other kinds of pollution type diseases that erupt due to high sewage content is also another possibility, and that's something that we'd like to address as well. And so physical damage, when you have boats going into the reef area or dredging going on in the reef area, or if you throw a stick of dynamite, you essentially cause the entire reef area to turn into rubble. And so that's essentially what you see. And this is actually very prevalent in lots of places in the Philippines. So cyanide fishing, you guys are familiar with that, and you squirt some cyanide in the coral reef area so you can catch the fish because it's stunned. But now what you also do is you actually poison the corals and cause them to die. And so you have a healthy reef there on the left, and something after exposed by cyanide, which basically causes them to get poisoned and die slowly. And so when reefs die, there's many net effects. One is that you lose all the fish, because the fish will migrate into a different area where there's more nutrients and there's more food for them to grow and also for protection. You also have fishermen. They don't have any more fish catch, so they have to go further and further into the deep sea. And so that causes economic stresses to their families. They can't feed their families adequately. They have to spend more fuel, more for netting to catch actually fishes that was used to be readily available right next to their coastal community. You also have issues with beaches and shorelines being washed away because now you don't have the corals to stop the waves or slow the waves down from breaking on the shore and causing erosion on the coastal areas. So actually lose beachfront area with this. Tourists are a very big economic benefit for coastal communities when they go there to go diving and snorkeling and enjoy the entire marine ecosystem. And when you have corals basically destroyed, you don't have that beautiful ecosystem that tourists can appreciate. And so now we have problems with economic, not only fishermen livelihoods, but also tourism livelihoods. It's a double net effect that's actually negative in the part of the coastal community and the economy in general. And so that's why we think we have a solution for the corals that are, if you want to say, feral or in trouble. And that's what we call the BioRock process. And I'll show you more about this. So what we do is, BioRock, we essentially do mineral accretion or mineral deposition. And so what we do is we apply a low voltage electricity, DC electricity, so inapagyan ang kurente underwater into a metallic structure. And then ang metallic structure we apply a negative terminal or negative charge in the metallic structure. And so you have a negatively charged metallic structure that's conducting underwater, and then calcium ions in the seawater are dissolved everywhere. So there's 5 abundance of calcium ions. And these then are attracted to the negative charge because calcium is a positive ion. And so it's attracted to the negative charge in the metal that then deposits calcium. So you have initially a bare metallic structure that then gets deposited with calcium on the surface. And so it's actually calcium carbonate. It's formed, CaCO3. And then when calcium adheres to this and grows quickly, we can then attach corals on the surface. And the corals that are attached actually grow faster, 5 times faster, and are actually have better survivability or better, resistance to coral bleaching at high temperatures. So here's like a schematic of what we're doing. We have a solar collector or an energy system, in this case solar, or quite a windmill, or quite a land-based electricity, that you then connect the negative electrode to the bio-rock structure, which is the mesh, and then you have a positive counter electrode, which is basically an inert electrode. And then what you do is you pass electricity through it, and when you pass electricity through it, it'll accumulate calcium. And then that's when you then tie coral fragments onto the surface of this bio-rock structure now. And the bio-rock structure is now really the negative electrode. And so here's one of the prototypes that we built in Salle. We're using now a tidal turbine. So when tides go in, and so it's high tide and when it's low tide, the water currents shift with it. And so when you have water currents shifting in and out of the coastal area, you actually can use the water currents to drive kind of a water windmill, if you want to call it that. And so the picture there on the right, figure 2, essentially is a tidal turbine where when water passes through it, it'll actually start to spin. And so what you can do is you can turn this spinning motion and connect it to an electrical alternator with a drawing on the left. So the alternator can then now convert the mechanical energy, the motion energy essentially, into electrical energy, and then feed the electricity that's obtained from the alternator into the bio-rock. And so the bio-rock structure is there. You have a negative structure connected to the large metallic mesh, and then you have a positive structure that's essentially inert. And so all the calcium ions will stick on that negative structure. So another way of powering this is to use a windmill, and I think many of you guys are familiar with windmills. They're used to here in Hollow and the farms to pump water from the ground. In our case, we don't use it to pump water, we use it to create electricity, which we then, again, apply to the bio-rock structure to accumulate calcium, which we then will tie up with corals later on, so that the corals that are tied on the bio structure grow faster and also are more survivable, so that we now can bring back the fish. And so when the fish come back, basically now have a better ecosystem that has corals, small shrimps, snails, crabs, lobsters, eel, and fishes as well, which is now not only a tourism draw, but also a good livelihood for fishermen. Another method that we're actually using now is we're using solar power, the power of the bio structures. And so again, the same setup. And why are we using tidal energy, wind energy, or solar energy? Because they're non-polluting, number one, and also you can actually put them anywhere very, very far away from shore. So if you were to use, let's say, electricity from Senegal, and you were to run electric wires directly to the reef, sometimes the reef is 1 kilometer or 2 kilometers away from shore. And so that means we need a lot of electric wire, which is very, very expensive. Also, the electricity that comes from the electric grid on the land is typically from coal-based power or petroleum-based power plants. And so that means you're actually still emitting carbon into the atmosphere, causing more global warming. So in our case, we're a non-polluting energy source that's renewable, and also we can site our system better because we don't have to run very long electric wire. We can put the solar panels right above our vehicle when we need it, and then run the power that's generated from it directly into the reef. And so here's 2 pictures of the bio-rock that we're building. It's made of camellia, basically. The things that are made of the ceiling or the covered court is essentially what the rebar or the bio-rock is made of. So you shape it into any form, into any design you like. So now you're actually doing like seascaping. When you do landscaping on land, create undulations and contours on that, say, a garden or something to make it look nice. We can do the same now with a bio-rock. Shape it depending on the way the seabed looks. If the seabed is very tilted or very slanting, we can do a bio-rock that's low and close to the seabed so it doesn't fall over. But if the seabed is, let's say, flat, you can do a high structure where you can put many holes in it so that you can now have divers go in and fish hide inside. So here's 2 designs that look like, kind of the bowl not upside down, or salikot, that looks like a cone, not upside down one. Here's another one that looks actually like a flower. If you notice, the pieces that are sticking out in the back look like the petals of a flower, and then in the center there's a large circle. So it's like a big, flower that's opened up. And they actually have floaters in the center of this one now because what they want to do is they want to carry it into the reef area where they want to put it and then cut off the floaters and then let it sink. So here's a picture of how they do it. They build the bio-rock on land and then they float it into position and then they drop it into the reef that they want to restore. And then the next thing to do is you attach the electric cable from the solar panel or the windmill or the tidal turbine, so you can now deposit the calcium when the electricity is flowing. And so now, the rebar, from plain rebar that looks like this, bare, black or red or whatever color it may be, has now a white coating on the surface. And that's now the calcium carbonate that's formed. That's essentially the building block of the coral. So corals are white because they're made out of calcium. What we're doing is, if you want to say, similar to on land where plants, they fertilize so that they grow faster and more sturdier. We're essentially, if you're going to say, fertilizing the coral by putting down a layer of calcium, which they can then use to grow faster with. So it's like a fertilization type process to increase the growth rates. And then that's what you do. Naturally broken pieces of coral, then you wire onto the structure so that you can then monitor it for how fast they grow. Typically, corals grow on the order of 1 centimeter every 2 to 3 weeks. The bio-rock-based or bio-rock-assisted corals have been shown to grow up to 4 centimeters every 2 weeks. So it's a 4 times growth rate, which can then really accelerate the regeneration of corals in a small environment, a small location. We don't plan to, cover the entire Negros island shoreline with bio-rocks, but if we can have, good coral regeneration in a small area, maybe what we can then do is, try to repopulate that area, and then as the fish density goes higher, it can also spill over to the outside areas and also, create like a hatchery type condition where there's a hatchery of corals that then receive or repopulate the neighboring areas. And so there you go. Now you have coral fragments that are now covered over the entire frame. And so you have here, in this case, you have large circles so that, you can have fish go in, and you can also have divers go in and observe these. And then that's when we monitor for growth. We have a ruler, literally. You go down and you take a picture of the corals after several weeks to see how fast they grow over time. And so here's an example we have in the Maldives, which is near India, south of India. The Maldives actually is very, very lowland, very low average land area, I guess, in terms of how high sea level is there. I think the average land altitude is even below sea level. So it's very imperative that they actually, keep their coral reef areas, I guess, alive, because if not, the waves will start to cover the entire islands and cover them. And actually, global warming is a very big threat to the Maldives, which is a big tourism place. And so, what they did was they created, a bio-rock structure, like a kind of a cone that's stuck on the side. And then what they did was they seeded it with corals. So they took coral fragments, or in this case, large coral pieces, and put it on the bio-rock structure, so that these can now grow faster. And so they monitored it for growth after a year. And then after 2 years, and so you can see after 3 years, a full bio-rock structure that's covered with corals. And so now this is a balanced and rich ecosystem. The fish can come in, tourists can go in and dive around it, and and help the local fishermen catch fish. And so that's why we want to use the bio-rock process here at Salle, so we can actually do very fast regeneration of corals in the area, given that they now have a marine reserve to actually protect the area from destruction. And so, why are we growing corals? Again, it's because we want the fish to come back in, because it's the fish that, fishermen feed off of, and we actually feed off of, given that the Philippines is a very, very big fish, economy, fish protein economy. And so now you have a marine ecosystem that is most balanced by corals and fish, so they're basically, it's a complete ecosystem, not just, I guess, an ecosystem that has only fish because you put down structures that are just tiny pieces of fish. Now you actually regenerate it or reseed it with corals as well, so it improves the entire ecosystem. And so in addition, the tourism aspect is actually a very important point to draw on, because tourists brings money to the local economy. And so we can build a lot of bio-rock structures that look attractive to the tourists. What we can then do is really bring back tourism to Salle, give it now a marine museum, which I encourage you all to visit, and then, so that they can go now, look at the museum, see the situation about the marine ecosystem of the Philippines, and then go take a look and dive in the bio-rock structures that we have in Carbon and Volcano Reef. And so the bio-rock process or project or method has been implemented in different places around the world. And it's the first time in the Philippines that we're actually using 3 different energy systems, solar, wind, and tidal, because we want to assess what kind of growth rates we get using the different energy systems that are available to us, but are not polluting, very importantly. In a lot of places around the world, they just use electricity from land and pump it into bio-rock, so it doesn't really help overall the environment. There's still a net effect on the carbon being emitted by the power plants. In our case, it's zero pollution, and we're autonomous from the grid. And so it really allows us to do coral reef restoration where there's ideal sites for, just like in Salle. In Salle offshore, there's no more electricity there, and so that's why we need to put in our own solar panels and windmills. The project, the bio-rock project, has actually won many awards, international awards around the world. And the latest one that has won is the MIT Ideas Competition. So I'm a student from MIT. We wrote a proposal to try and restore coral reefs in Salle, because the economy, the community in Salle is very progressive. There's a very strong push for preserving the marine ecosystem. And so by writing this proposal, we actually won some funding so that we're now here and implementing a project in Salle. And so with that, I'd like to thank you for your attention, and I hope we can work together to support you.
Thank you, DJ. By the way, DJ is flying back to Massachusetts tomorrow. Yeah, Thursday. Why we are doing this? Because the 4th quarter of our RHGP is scheduled to discuss about environmental issues. And I think we are privileged to have him this afternoon to talk to us about the project. The grade 10, 11, and 8 that have this, only grade 9 who would fit in the schedule. So anybody from the audience who would like to ask questions about the discussion this afternoon? Yes, Trina, please come. Patricia.
Who came up with the bio-rock idea?
The bio-rock idea was initially invented by Dr. Tom Barrow, the partner, our American partner, who's has been a marine biologist for the past 20 years, and he had met with other people doing marine, coral reef restoration projects, and they came up with this idea of being able to put down calcium on the surface of metal. And so he's really the inventor of bio-rock. In our case, we're innovating it in a way that we're not using electricity from the ground or from the land to power bio-rock. We're now using renewable energy, alternative energy, which is not polluting. So, they used land-based electricity to power these systems previously, and we said we can do even better by using renewable energy and being able to use these systems so we can site the bio-rock projects in different areas of the Philippines that are very remote and far away from the coastal shores.
Another question? Yes, Guido, please come forward.
Can you get involved in the project? Yes, you can actually get involved in the project. Right now, we just finished our construction activities. These are some of the pictures that we have from our installation activities in Salle. So this is Enzo carrying one of the solar panels that we installed in Carbon Reef. This is the bio-rocks that we're actually deploying in Salle right now. Here's how we're dropping the bio-rock structure now into the sea area. Ila, Martin, and Enzo on the top of the roof of one of the ranger stations in Salle. So we put down the solar panels on top of the ranger station so they don't get wet by the seawater. And now there's also actually a marine guard that protects this 24 hours. So there it is. The solar panels are connected on the top of the roof. And then the bio-rock structure is actually located 100 meters away from the shore. And here's a picture of us creating the MIT logo for our school. let me see. And so here's a picture of the wind turbine that we installed. And so how you can get involved is in partnership with your teachers here. You can encourage them to talk to the folks in the Salle Marine Reserve and the Children's Museum to try and start up a small bio-rock project. What we do is, given that we have a large-scale installation for bio-rocks right now in the Marine Reserve area, what you can then do is connect a small metallic structure that your class can build, for example, connect it with small corals that you have measured and understood, and then connect it to the large bio-rock structure, and then have electricity feed into it, and then mushroom grow on it. And then what you can then do is, over several months, you can then measure the growth rate of the coral, and then different classes can have different designs of the bio-rock, given that it's small and lightweight, and then this can be deployed by each class as a science project. So I think Mrs. Ryan, Dylan and others will be able to, fine-tune these details.
Actually, your science teacher was missing a while ago. So maybe the class could talk to Sergi about Miss Mel. If you want to help get involved in the project, that's, I think, possible. Yeah, okay. And I think that's one way of getting directly involved in this kind of project. Okay, so we'd like to ask Sir Romy, our grade 9 moderator, to give the certificate to the
for the students and like to award the certificate of appreciation with University of St. Salle OFCT has a department. Certificate of appreciation is given to our guest speaker as a resource speaker of the topic first step for project is the bio-rock method. To the grade 9 RHGP classes given on the 23rd of January 2007. Signed, Dominic Server, grade 9 moderator, and is Lord of the National 2007. Sir, thank you very much.
I would like to call on again Marian Taver, the grade 9 governor, to give the word of thanks on behalf of the grade 9.
On behalf of the grade 9 students, I would like to thank Sir GJ for giving us the talk on the bio-rock project. Thank you so much. Let us all remember that we are in the most holy presence of God. We thank the Father, the Son, and the Holy Spirit. Lord God, we thank you for giving us this day. Thank you for letting Mr. GJ Lao to share his knowledge about the project, and may you always guide us. Saint John Baptist of the Son, with Jesus in our hearts. Thank the Father, the Son, and the Holy Spirit.